video is about symmetry of functions. And so functions can be symmetric about the y-axis, and they can be symmetric about the origin. There's also something called symmetry about the x-axis, but in those cases, those are not functions because something that's symmetric about the x fails the vertical line test. So when we're talking about functions, mostly we just talk about something being symmetric about the y-axis and symmetric about the origin. So number 2 on your worksheet I have here. Also on your worksheet, you see all these X's? That's a problem I didn't want us to bother with. That's all that means. So I X'd it out. Symmetry about the y-axis. When you have a graph, it's super easy to see. You just look at it. You don't do anything. You're just like, does it look the same on both sides of the x-axis? That's what you're asking yourself. So when I look at number 2, mine is not perfectly drawn, but if it were, you would say, yes, I see a mirror image on both sides of the y-axis. So yes, that is symmetric about the y. So I'll say yes, yes, this is symmetric about the y-axis. Now, let me just tell you other ways that people say the same statement. If something is symmetric about the y-axis, they might just also say it's got y-axis symmetry, or it's symmetric with respect to the y-axis. They may say that, but it all means the same thing. You can say it's got y-axis symmetry, it's symmetric about the y, or symmetric with respect to the y. So let's see. How about this? Look at number 4. Just look at it. Does it look the same side on both sides of the y-axis? No, it doesn't. Because if it did, I would see another part up here like this, and I would see another part down here like that, and I do not see that. So this is no y-axis symmetry. Okay, look at number 6. Now, this is not a function, so it could have x-axis symmetry. And mine is not perfectly drawn, but I did my best, and that is my best. Sorry about that. But anyway, is it look the same on both sides of the axis? If you look at your sheet, it does. Okay, and mine is trying to look that way. So we would say yes, y-axis symmetry. Y-axis symmetry. So let's just go ahead and talk about x-axis symmetry. Does it look the same on both sides of the x-axis? And it does. So this also has x-axis symmetry. But you only get that. For graphs that are not functions. If you recall the vertical line test says if you can pass a vertical line, it hits more than once, it's not a function. And so this is not a function. That's the only reason we could get x-axis symmetry on a graph. Okay, now that is what y-axis symmetry is, symmetric about the y. The next thing we're going to look at is, we discussed, okay, x-axis symmetry. It looks the same on both sides of the x. The next one is symmetry with respect to the origin, or origin symmetry. So how do you do that test? This is how you do that test. You must kind of reflect the graph about the x-axis and then reflect it about the y and see if it lands in the original space it did. So let's just look at this. Look at number 2. What if I reflected this about the y? Okay, if I did that, here's my intermediate picture that I'm going to draw. If I reflected about the y, it looks exactly the same, right? So we did about the y, okay, done. Now let's reflect it about the x. If I reflect it about the x, what's going to happen is I'll have a mirror image. So let's see, I'll have this will be going, oh, it's so hard for you to see this. This would be like this. Be like this. It would come down and up and down and up. This would be reflected about the y. Does the red graph land in the original place that the black graph did? No. So this has got no origin symmetry. All right, let's go again. Let's look at this guy. The test for origin symmetry is to reflect it about the x and then the y, or vice versa. The order doesn't matter. So let's look at this guy. Let's reflect him about the x. So this part's coming up here, and this part's coming down here. So that means that this will look like this, and this will look like this. Okay. Now take this reflection and reflect it about the axis that you haven't done yet. So take this side and reflect it about the y. This will fold over here, and I see it's going to match right there where that black part is. And this is going to fold over here, and it's going to match where that is. And it did land in the original spot. So this has origin symmetry. Just like that. Okay, what about this guy? Does this have origin symmetry? Now, this is not a function, so usually we don't use this talk for not, but let's just do it for kicks. Reflect this about the x. Okay, looks the same. Reflected about the y. Okay, looks the same. We would say, yes, it has origin symmetry. Okay, here's a few more graphs for us to do that with. Let's just see what we can figure out. Look at 34. Just look at it. Does it have y-axis symmetry? It looks the same on both sides of the y-axis, so we'll say yes. Y-axis symmetry. So now let me let you off the hook a little bit. If a function has y-axis symmetry, if it's a function, then it will not have origin symmetry, and it will not have, it will either have one or the other. So this is a function. Since it has y-axis symmetry, I don't even need to check for origin symmetry. So we're done. Okay, look at 36. Does this look the same on both sides of the y-axis? No, it doesn't. If I did, I would see a picture over here, and I would see a picture over here, but it doesn't. So this is no y-axis symmetry. Okay, now let's test for origin. So let's reflect it about the y. If I reflect it about the y, then this piece is coming over here, so this will look like this. And this piece is coming over here, so this will look like this, and it'll still have that same open circle right there. Now reflect it about the x. What's going to happen? This piece is going to fold up here. This piece is going to fold up here. Right here. And this piece is going to... Did I do that the wrong way? No, I just did that. Okay, let me start over on this one. I'm messing this up somehow. All right, sorry. So, this is real life. This is how it goes. So, let us reflect it about the x. I'm doing the x. So, if I reflect it about the x, this piece is going to come up here and have an open circle there. And this piece is going to come down here and I have a closed circle there. Okay. Then let's reflect it about the y. If we reflect about the y, then this will come over here. Come over here, and this will come over here. And this would almost have origin symmetry if it weren't for that open circle. Because we're going to have an open circle where there was a closed circle and a closed circle where there was an open circle. So that doesn't match exactly. And so that is what preventing this from having origin symmetry. So we'll say no origin symmetry. Now, if this had come to us and it had been a closed circle and a closed circle, then yes, it would have origin symmetry. So if that were the case, then it would. Let's look at 38. Let's reflect it about the x. If I reflect it about the x, then this guy's coming up here like that. And this guy's coming down here like that. And then we're halfway through the process. Reflect it about the y. This will come over here and match the black. This will come over here and match the black. And so we'll say yes, origin symmetry. What can we say about y-axis symmetry? Well, if it's got one, then it won't have the other. So no y-axis symmetry. Okay, now, we give names to functions that have y-axis symmetry. Any function that has y-axis symmetry gets the name an even function. So let's go through and see, can we name anybody even? All right. First off, it only applies to functions. So this is not a function, so no, I'm not even going to talk about you anymore. Okay, Lizzie, did this have y-axis symmetry? It sure did. This was me doing a different test. It does. So this is an even function. This one's even. Did this have y-axis symmetry? No, he doesn't get the label even. Did this one? Yes, he gets the label even. Did this one have y-axis symmetry? No. No, they do not get the label even. So, and if we want to say not even, you could even go and say, okay, this is not even. If you wanted to say it doesn't get the label even. Now, if a function has odd symmetry, If it has origin symmetry, we label it an odd function. So since the function can't be both y-axis symmetric and origin symmetric, it cannot be both even and odd. It will either be one or the other, or it won't be anything. So right here, since this was even, it is not odd. Now, did this one have origin symmetry? Yes, it did. So he gets the label odd function. He's not a function. Don't even talk about him. This was even, so we know he's not odd. This was not even, and when we did it's not odd either because it did not pass the test for origin symmetry. So this is not odd. So sometimes in textbooks they'll be saying it's label it either odd or neither. Neither is not really anything special. It's just saying that it is not even and it's not odd. Over here, did it have origin symmetry? Yes. So this is an odd function. So that's the even odd talk. And when they give you a graph, it's super easy. Now we're going to tackle how to tell if something's an even function or an odd function when you're just given the algebraic representation of it. So let me write those functions down and we'll figure that out. So we just have a few functions to look at here on your sheet. So we're supposed to determine if they are even or odd, or not even or not odd. So this is the test that you can do. Oh, it takes a minute to erase this little border. Okay. So what if we are given this function right here, f of x is, no, I lost my sheet. That's not going to help. Oh yeah, I found it. F of x is equal to, let's see here, 7x cubed plus 4x minus 2. Or f of x is equal to x plus 1 over x. Or f of x is the cube root of x. Or f of x is 1 over x squared. And I'm just going to add a bonus problem. F of x is 3x squared minus 2x. Okay. Let's look at that. So here is the test to see if something's even or odd. The test is you evaluate the function for negative x and see what happens. Evaluate the function for negative x and see what happens. So if you put in negative x and after you simplify and evaluate it, it looks exactly like the function did originally. That function has y-axis symmetry, and this is an even function. If you put in negative x and you simplify it and you notice that it's equal to exactly the opposite of the original function, this is an odd function. It has origin symmetry. If you put in negative x and it doesn't look like either one of those things, then it's not even and it's not odd. So here we go. Let's look let's do the test for the first one. F of negative x is equal to 7 times negative x cubed plus 4 times negative x minus 2. So this is equal to negative x times negative x times negative x is what negative x cubed is equal to. So a negative times a negative is a positive. A positive times a negative is a negative. So what we get out here is 7 times negative x to the third. All right? Plus 4 times negative x is minus 4x minus 2. This is equal to negative 7x cubed minus 4x minus 2. So this is what f of negative x equals to. Now we'll look at it. Does this look exactly like the original? Well, I have a positive 7 there and a negative 7 there, so no. The one thing I can say so far is this is not even. Not even. Okay. Does this look like the opposite of this? What is negative f of x? What would that look like? Okay. Negative f of x would look like this. Negative f of x would be where I change the signs of all these. Negative 7x cubed minus 4x plus 2. Does this result look exactly like this? Negative x, 7x cubed minus 4x, uh-oh, plus 2 minus 2. No, it's not exactly. So we would also say it's not odd. So I want you to notice something. Just because something's not even does not automatically think it's odd. You have to check for both. Okay, let's look at this one. F of x is x plus 1 over x. The test is to put in negative x. All right, this is going to be a negative x plus 1 over negative x. So this is negative x minus 1 over x is what I get. Well, does this look exactly like this? No. So we can say not even. Not even. However, what is the opposite of the original function? What is negative f of x would be negative x minus 1 over x. Does this look like this? Yes, it does. So we can say that this is an odd function. So that's what we get there. All right, cool. Let's go ahead and do this one, the cube root of x. So, the cube root of x. Let's just think about this for a second. If we put in negative x, this would, okay, what would f of negative x look like? I'm getting all the colors mixed up. F of negative x is going to be the cube root of negative x. All right. The cube root of negative 1 is equal to negative 1 because negative 1 to the third power is the same thing as 1, and when these two match, you can pull out a negative 1. So what happens when you have a negative under an odd index, an odd radical, is you can just pull out a negative 1. So right here, this negative, I'm allowed to pull out a negative 1, and then this is the cube root of x. Well, we can probably see this one pretty easily. This is not the original function, so we'd say it's not even. But it is exactly the opposite of the original function, so we would say that it is odd. That's an odd function right there. All right, I changed my mind. We don't need to do this last one. I thought we didn't have a good example, but we saw what I wanted us to see in number 1. Let's do this last one. Let's plug in f of negative x and see what happens. We get 1 over negative x squared. All right, 1 is still a 1. A negative times a negative is a positive, so in the denominator we get x squared. Does this look like the original? It certainly does, and so this is an even function. This is an even function. So if it's even, we know it's not odd. So that is the test for even and oddness. Now, sometimes you can tell ahead of time what's going to happen. And so if you have a polynomial, which is something like this, right? If you have a string of terms, the power on the x is a 3, which is an odd number, and the power on this x is a 1, which is also an odd number. And this 2 technically is x to the 0 power. If you have a mix of odds and evens, then it's not going to be odd or even. But look at this one. The power on the x is 1, and the power, even though it's in the denominator here, is 1. Since those are both odd, it turned out to be an odd function. You can kind of see that coming sometimes. The power on the x here is even. You only had an even one. It's going to be even. So sometimes you can tell ahead of time if you don't have like a complicated function. All right, that is symmetry.